So a temporal processing hierarchy for narrative in the human cortex. So this will become meaningful to you as the presentation goes on. In the beginning, we'll start off with something kind of interesting. This is the immediacy assumption. So in human language comprehension, during language comprehension, all available information will immediately be used to co-determine the interpretation of the speaker's message. So that means even as you're understanding what I'm saying right now, you're using the words as you hear them, but you're also accessing information earlier in the sentence, but even earlier in the paragraph, and even earlier in your world knowledge. So there's a paradox as to how can we have immediate access to knowledge on all these different timescales. And so this point was raised in psycholinguistics by Haggard, based on work of Justin Carpenter. So we're going to try to address this puzzle. Oh yeah, and so this puzzle about time and space. So it's just noteworthy that LLMs continue to increase the context window size. So initially context windows were 500, 1,000. Now they're jumping up in orders of magnitude. It's probably 10 to the 6th now for some models. So one way to solve this problem of how do you have immediate access to multiple timescales is just to give yourself all that information on multiple timescales at the same time. But the brain has a context window of size 1. We get one word at a time, one after another. So how does the brain access context over extended time? You could imagine that to understand something based on a chapter in a book that you read yesterday, it would take lookup time to gain access to this information, but yet we have access to it immediately. So the answer to how we have access over extended time is by using a specialized architecture that transforms time into space. This allows for processing of multiple timescales in parallel. And so I'll try to convince you that the brain is a form of temporal to spatial transformer. It takes a sequential temporal input and transforms it into a spatial representation. So this allows immediate access, but how does it work? So to get to how it works, we're going to look at some neurophysiological background. So I'll show you data from 3 human fMRI studies that show how the brain processes multiple narrative timescales in parallel. And then we'll try kind of in the Feynman sense, I cannot understand what I cannot create. We're going to try to make a model that can simulate this processing in multiple timescales. And then there'll be some discussion about that. So the first one, this is from a study by Baldessano and colleagues in 2017. So they had the subjects in the fMRI scanner watching episodes of the Sherlock movie, and they took brain activation during this about half-hour long fMRI experiment. And what we see here is time point correlations of activity. So they take this area in the visual cortex, a certain number of voxels, make a vector out of those voxels, and then measure the autocorrelation between that vector of activity over time. And so what you see here is rapidly changing correlation. So the structure of activity in the brain follows more or less the structure of visual input in the movie. Whereas in this higher associative area, we see that the time point correlations are coherent over time for up to a minute. So that corresponds to scenes in the movie where things are happening. There's some kind of semantic continuity, even though the visual image might change. There's this semantic continuity showing that this part of the brain is representing events at a longer time scale. So we have these multiple time scales of representation at different regions in the brain. Does that make sense? Another example, so I'm going to give you these 3 examples of clever experiments that people did to show these multiple time processing scales. So in this experiment, subjects are listening to a narrative that's intact. In this case, A, B, C. So these are different sentences in the narrative, one after another. So there's the intact group, and then the scrambled group is getting those sentences in a swapped order. So that's going to create a situation where the two groups are going to hear the same sentence E, but preceded by two different sentences. So they're hearing different, and then at a certain moment in time, they start getting the same input. So what you can do is measure the correlation of activity in different brain regions in these two groups of subjects at that transition point from when they're hearing different input, so the brain activity should be different, than when they start hearing the same narrative input driven by the same input, the activation in the brain regions should begin to converge and become aligned. And so what you can do is measure this alignment time in different brain regions. And finally, we see that in the auditory cortex, the alignment is happening after about 4 seconds, whereas in successively higher level brain regions, the alignment takes more and more time. So the idea is that this is another manifestation of this temporal processing hierarchy, where we see that things are happening quickly in input-driven areas and more slowly and slowly in higher associative areas, where in principle, that's where the making sense is going on. And then the final example that I want to show you, again, is showing, in this case, similar neural responses across different brain networks that occur with a gradient of delays. So it's the same kind of experiment where people are listening to auditory narrative in the scanner. And in this case, we're going to take activity in one area, the dorsal language area, and find the correlation between activity in this area and these other networks in the brain, find the maximum correlation, and then find at what temporal lag does that correlation occur. Is the correlation aligned in time, or does it occur after a certain delay? And then you can order these different brain networks, the auditory, ventral language, dorsal language, default mode network A, attention, and default mode network B. So this is a hierarchy of increasingly associative areas where, in principle, more higher level cognitive processing is going on. And when we look at this, this lag matrix, where basically every cell is showing what's the temporal lag between network 3 here and network 5. So network 3 and 5 are correlated 6 seconds after the input is presented. And so we can see in this lag matrix the structure of temporal processing across these different networks in the brain. So these are neurophysiological manifestations of the temporal processing hierarchy, and we'd like to understand, where do these come from? And it's kind of a chicken and the egg question. Do higher level processes like making sense take more time? And so that's why they occur with this temporal lag. Or is there some structural organization of the brain that produces this temporal lag and then allows those processes that need more time to occur in those networks? So we see these three studies that I showed you. Different brain regions segment in different size events. Different brain regions construct the narrative context with different time constants, and then the correlation lag between these different regions varies along the same continuum. So these are the phenomena that we're interested in. And the question is, so we're going to have a computational model of cortical processing where we're going to try to see if we can simulate these phenomena that we're looking at. And so if there's one characteristic that you wanted to use to characterize connectivity between neurons in the cortex of the human, it's local connectivity. So this is a graph showing if you inject a dye into a neuron and then measure what are the distance between it and neurons that it's connected to, highly connected, number of connections, very local, and then 2 millimeters away, that starts to drop off. So neurons are predominantly connected to their local neighbors. So you can translate that into a recurrent neural network where neurons are connected to their local neighbors. And this is kind of the birth of a form of reservoir computing. So the reservoir is a network of leaky integrator neurons that are connected by local recurrent connections. And these reservoir units are going to input, they're going to integrate the input signal over time and generate high dimensional representations of the input because of these recurrent connections. So the inputs are mixed. So you're going to get mixed selectivity and rich structure in space and time. And so already they have an interesting property in the reservoir itself before you try to do any learning. Typically learning is learning the associations between patterns of activity in the reservoir and the output neurons for the task that you're interested in. But just looking already in the reservoir, there's these interesting properties, including sensitivity to time. So we're going to use this kind of network to simulate narrative processing. So how are we going to do that? Here's the reservoir network. So we're going to take the input narrative, like the narrative that was used in these experiments that I was showing you. We take the transcript of the narrative. For every word in the transcript, we can use an arbitrary language model. We use the Wikipedia to VEC, which is a language model trained on Wikipedia. So for every word in the input narrative, we get the embedding. So that creates a trajectory of embeddings that's the input into the network. And that's going to generate a trajectory of reservoir patterns of activity. And that trajectory of patterns of activity inside the reservoir is a proxy for human fMRI activity. So we can do the same kind of analyses. Here we can do this time point correlations and see different periods of coherence when there is probably common semantic structure, common vectorial geometric structure in a sequence of embeddings that's talking about a coherent narrative. So we can use that model and we can now go back and say, okay, so how would we simulate this experiment using this model? So what we can do is simply do the same experiment on the model. So we have two versions of the model running in parallel. One is going to get the intact narrative, one will get the scrambled narrative. We take the pattern of activity in the reservoir during the presentation of the whole narrative and subtract one from the other. So in this case, the two models at this period are getting the same input. Now they're getting different input. Now they're getting the same input. So if we subtract the reservoir activity of one from the other, during the period where they're getting the same input, the activity is identical. So there's no difference. This is the difference when they're getting different inputs. And now this is the interesting period where they begin to get the same input. So just like in the human experiment, they've had different input, now the same input. And so we see this, this alignment that begins to occur with the time constant. And so we're going to say, oh, what is the time constant here? What's going on here? So what we can do is sort these neurons by their time constants. And so we see a nice distribution of time constants of this integration across the 1,000 neurons in the reservoir. Some of them fast, so rapidly responding, some of them quite slow. And if we go back and do this analysis with the hidden Markov model, we find the same result as in the Baldessano study. That is, the fast neurons have a rapid event structure chopped up in time, like the structure of the input. Whereas the slower neurons have this more extended event structure, as if they're representing some kind of semantic continuity in the narrative. Yeah, and feel free to ask questions. So again, kind of reproducing this effect. However, if you're paying attention, you say, yeah, but what you showed is neurons in the same reservoir that you had to sort in order to get these different temporal effects, whereas these are neurons at different locations in the reservoir. So how can we do that? So then we could introduce this notion of topological structure into the reservoir. That is to say, we're gonna actually more strictly obey this rule and say we're going to reduce long distance connections in the reservoir. So we're going to say we're going to have input projected to a subset of neurons, and then really only local connections between neurons within the reservoir, which gives this kind of canal-like topological structure to the reservoir. So the information has to flow from one end to the other. So this is the connectivity of neurons to and from neurons in the reservoir along the diagonal. So showing this local exponential distance rule connectivity. So if we do with this topology, now we no longer have to sort the neurons. If we just take the time constant, the integration time constants for arbitrarily sized groups of neurons binned into groups based on their distance from the input, then we see this nice hierarchy of time processing time constants for narrative processing in this hierarchy. So that's interesting, but we know from the human neuroscience studies that the story is not quite so beautiful as this. So for example, there are areas in the human frontal cortex that are far from the auditory input areas, yet that have a processing alignment time that's almost as fast as the sensory driven areas. So how could that be? How could you have areas that are distant that have to traverse all these local connections that still have a rapid time constant? One hint as to how that could be resolved is that is shown here. These are white matter connections going from input-driven areas directly to these frontal areas. So there are shortcuts, white matter pathways in the cortex that could provide an explanation for this rapid processing in these frontal areas. So in fact, if we introduce a shortcut into the reservoir with this connectivity matrix, so you can see we're adding some connections here from early input-driven areas to these later far-away areas, then we see that in this later far-away area that's now getting input from the input-driven neurons, the alignment time is reduced. So we're starting to see that maybe these temporal processing hierarchies in the brain can come from structural properties of the network. That was very simple structural processing, structural properties, where we're very grossly simulating human connectivity. What if we use the real human diffusion imagery to get a real human connectome and see what happens with this temporal processing hierarchy in that case? So with the colleagues in Marseille, we did a study taking from 100 human subjects their full brain practography, so you can trace all the pathways through the full brain and create the full brain connectome. And then you can also parcel out these different fiber bundles, like the frontal occipital, inferior frontal occipital fasciculus, the arcuate fasciculus, different pathways that are known in the human. So we can isolate how these different pathways are represented in the connectome, and then run our experiment on a reservoir whose connectivity structure is now using the human connectome. So I must admit that when we did the very first simulations with this, I was like, oh, we are now using a human brain in the connectivity of the reservoir, which was pretty cool. So we can run one reservoir intact and one reservoir with removing one of these pathways, and then see what happens to this topography of the of time processing. And so when we do that, so for example, here we're going to remove the inferior frontal occipital fasciculus, and what we see is when we subtract the intact from or the lesion from intact, we see a slowdown of processing in these frontal areas. So this is an explanation of why in the human data we saw unusually fast processing in certain frontal areas, because they're getting access to this kind of shortcut processing. And so if we look at this graph shows the alignment time versus the Euclidean distance from the input. So basically, as you get farther from the input in the brain, the alignment time increases. And these black X's show these areas that are shown in the that were affected by the removal of the pathway. So they're beneath the diagonal, kind of unusually fast. And when we remove the shortcut, they move back up to the diagonal, so having a processing time consistent with their distance from the input. And then finally, just to finish, we go back to the third study that I showed you, where we measured, where Chang and colleagues measured the correlation between different networks, and then what was the time delay required to find that correlation, and showed this lag matrix. So we can do exactly the same experiment with the model. So we have the reservoir with neurons just binned into groups of neurons successively far from the input. We measure the correlation between one bin and another, and then the time lag for that maximum correlation to occur. And what's interesting, we can do an experiment here that we couldn't really, or that they didn't do in humans. In one case, the input to the model was the embeddings shuffled at the embedding level. So that means that we completely, each embedding itself was shuffled. So all structure was removed from the input. So there's a hint of a lag gradient here, but it's very small, and that's a kind of a vestige of the physical properties of the network. Here we do word scrambled naturalistic stories. So now the embeddings are intact, but they're scrambled in time. So there's still some structure from the embeddings in the input, and we start to see the lag gradient emerge. And now this is the intact naturalistic story, and here we see a more robust emergence of the lag gradient. But so what that means is that it's not only the physical structure of connectivity, but it's the semantic structure coded in the vector structure of these word embeddings that's necessary to produce this lag gradient. And the way to visualize that kind of is that in the input, imagine that you're in a scene out fishing in the ocean, and then now we're inside in the warm cabin. So that those semantic vectors from the language model will be geometrically different at that transition. And that transition is like a pulse in the input that will propagate through the network. So you need to have this kind of intact semantic structure in order to be able to find the lag gradient in the network. So the idea is that in this case, time is transformed into space. We have this temporal sequence of words that's now transformed into a multi-scale representation in a physical spatial hierarchy in parallel. Depends on the structure of the network and structure in the input. It means that you have simultaneous access to multiple levels of temporal information from these different networks. It helps to explain how immediacy is implemented in the brain. Can this have implications for machine learning, AI? We don't know, but that's to discuss. And the final kind of tricky chicken and egg question. So the structural architecture creates areas or networks that have different specialized temporal processing windows. And then we can ask the question, is this what drives specialized cognitive processing in these areas? So for example, to do high-level integrative semantic interpretation, must you have an area that has this long time constant temporal integration? And so that's why when you do your fMRI experiments, you say, oh, narrative interpretation is done in this area. Because often, yeah, when you do that kind of interpretation of cognitive function, it's often more around the cognitive function and not about why is it at that location in the brain and not somewhere else. So this is a possible explanation for that. And eventually this could have impact in, or the question is, could this kind of treatment on multiple timescales be of any transfer value in looking at large language models and this kind of thing? And so I will stop there and hopefully answer some questions. Thank you very much.
So very interesting. One of the first questions, I mean, one question I have, because you often talk about semantic similarity.
Yeah.
But I was wondering whether in some of the studies they have investigated the case where you have sometimes different sentences, but and then it's the same sentence. But you could imagine different sentences, like in terms of tokens or words, but with synonyms, so that the meaning is the same.
Yeah.
And how that changed here. Have you studied this or?
Yeah, no, that's a good question. So, yeah, I'm trying to think. I think there are studies where that came close to that, where they asked subjects to paraphrase the story that they heard. So, and then they ask for other people to listen to this paraphrase, so it preserves the semantic content. And I believe that you do then find alignment, so it's not really, it's not identically linked to the words themselves, but to the semantic content.
And could it be that some of these regions actually no longer align because actually it was the word that was mattering, while for others it's really interpreted at this semantic level? Or I would have expected something like that, but maybe.
Yeah, say that again?
That maybe for some brain structures, they no longer align because the words are not the same.
Yeah.
They are really,
No, really?
while for others, it's really at the high level semantic.
Yeah.
Even if it's,
Oh, I see, okay, wait. Yeah, in the more truly input-driven areas, you would, since the input is different, the alignment might be modified, whereas in the higher level, yeah, that's an interesting question. We would ask.
I had a study in mind for your latest question by McClelland, 1995, which was that, yes, we need that temporal scale because to learn the big structure, we need interleaving different tasks.
Mm-hmm.
And do you want to include it in the study, or is it already an application of it?
So you mean like McClelland with the
Complementary learning system, I think. But it was at first between hippocampus and neocortex,
okay.
passing through motor neuron.
Yeah, and so there you're really when you start to involve the hippocampus, now you're getting way back in time. You have access to things. Although what's interesting is that you can, in these EEG studies where you have people listening to something like, in the morning, John had breakfast, he ate milk and socks. And when you hear socks, you get this response that's based on real world knowledge. So somehow we have access to that real world knowledge immediately, which is kind of paradoxical because you have to access that knowledge and say, what are socks? Do they fit in here? So, so that remains, this immediacy remains kind of an interesting question.
And he had an issue with that because of that immediacy, maybe for him, the neocortex could learn too fast and therefore not get that structure and suffer that catastrophic interference where the representation is just shifting to something else different completely. I don't know if maybe those kind of conditions can predict cognitive deficits, maybe, or learning deficits.
Yeah, but that raises the interesting question that, if you read a piece of text and then you're asked to interpret it, that meaning remains relatively stable. It's not ephemeral. But so that's kind of beyond the scope of what we're doing here, which is just to say, within the scope of the input that you've received, you have this distributed representation of time over space. And so that way you can immediately access whatever degree of temporal resolution you need to understand.
I had a question in one of the first experiments where you show the aligned inputs, and then it diverges, and then it aligns again, and you see how the two reservoirs align after the input is the same for both of them.
Yeah.
Do you have some experiments or maybe analogies with this kind of experiment with long and short-term memories? Like, could you imagine an experiment like this where they do not align after the difference? And could this be could there be an analogy here with long-term memory? So, yeah, that's the question.
So the long-term memory would allow for alignment to occur, or what?
No, would you have an experiment like this where after the difference part ends and you get the same part again?
Yeah.
You don't have this alignment in the output of the reservoir, and could you?
But we do have the alignment. I mean, it happens.
Yeah, but could you have some kind of inputs where you don't get the alignment in the end with the reservoir?
Well, if the two inputs just remained different, for example, that would be.
So you in this experiment you have the same input, then the different input, and then the same again.
Yeah.
Could you have an experimental design in this kind of setting where the same input at the end does not result in a convergence of the two models?
No.
No?
But, I mean, because the same input will drive those neurons in the same way, and so then they will converge.
Well, it's not so obvious. I agree because in a way, at the end of the second period, the dynamical system is in different states.
Yeah.
And you might think it's in a different basin of attraction, and
Wait.
even if further you get the same
Yeah.
input, it might stay in a different dynamics.
Yeah, indeed. So you could and that's a function of the kind of the gain of the input. So if the input, so in that case, you could imagine indeed, if you reduce the gain on the input so that it's still perturbing, it's still causing the system to fluctuate in an input-based way, but imposed on that is this previous dynamic state that was made here. Yeah, then you could probably titrate and find a zone where this could occur.
So I noticed that like you showed some different studies, and some use like multimodal narratives, like they will watch the movie.
Yeah.
And from what I understand, in other studies, it's purely auditory in the sense it's like a narration.
Yeah.
So does this in some way like have a big impact, like whether you have a narrative that's maybe even only through visual input or through both? Like, would you say that in the end the results would be the same, and it's just like more visible when it's like, for instance, auditory?
Yeah.
Is this even processing like the same regions of the
Wait,
brain?
no, that's a good question. Yeah, that's a good point. So of course, in the input-driven areas, there will be a difference, but there's a nice study where they show either movies or just the auditory input from two different, either people in a restaurant or people in an airplane. And indeed, in most of these higher level brain regions, you get activity that can be decoded according to whether it's in a restaurant or a airport, independent of the input modality. So at some point, you make a transition, perhaps gradual, from really input driven, but fairly quickly to meaning, and then it's no longer dependent on the input.
But in both of those cases, it is still a narrative that's presented through language, right? Or it's a movie that is really like only. I'm thinking, like this.
Like a silent movie?
Yeah, this famous example, like with the objects, that's kind of like a triangle chasing a circle.
Yeah,
And so there's no language, and even like the shapes are like, but there is a narrative, right?
Yeah.
Which is not verbal at all. So I guess maybe another facet of my question was like not only the modality in terms of vision versus auditory, but the narrative, which is either verbal or purely visual.
Yeah. And I would think, I have to check that, but you should see this kind of narrative, these similar phenomena occurring in the case of these social geometrical objects.
Okay.
Yeah, but that's a good question also. And at what point do you start getting meaning from the physical stimulus?
I have a question about the architecture of the reservoir.
Yeah.
I was wondering if it would be interesting to have a reservoir that has not the same density everywhere, like in the brain, actually, where we have some neurons that, like some brain areas where there are more interneurons and other more pyramidal neurons, and therefore to have a reservoir with maybe high density and low density, and for example.
Yeah, no, that's a great question. So it's the modeler's dilemma. What are the phenomena that are most pertinent to my question? And so one, what we can say here is, we're gonna leave the classic reservoir mechanism and go for some kind of structured connectivity matrix. So that's one step in a more realistic way. But another, like you're saying, is to say, well, in fact, each one of these nodes in the reservoir at this moment corresponds to a voxel in the brain. And so maybe we should expand. So that's another, to expand that out. And that would get partially to your point of different densities of neurons in different areas. Then you can start to look at layered structure and interneurons that you're talking about. And so from my own personal experience, when you decide to say, we're gonna have to introduce interneurons, then there must be some reason why you think like there's something missing and maybe this would do it. Like, for example, one thing also is that there's a mix of inhibition and excitation. So we have neurons that can be with a TAN-H output function, so they can be negative activity. So then you could say there's no such thing as negative activity, but it could be done by activating an inhibitory interneuron. And so at that point, that might be a reason to say, okay, let's take that step and try to be a little bit more realistic. So realism is good, but it's always a pain. And so you have to decide that you're doing it for a reason.
I think we have other questions, but in the interest of time, thanks again.